The true method of knowledge is experiment. So said British painter and poet William Blake. Trying new things is inseparably linked to innovation. This includes innovating new ways to solve old problems better, as well as innovating new ways to solve new problems. I'm Ann Milley, your host for today's event, and we are in for a treat to hear about some compelling, creative, new ways of doing designed experiments, new applications. Some are solving old problems better, and some are solving new problems. If you have questions, please submit them in the Q&A and we'll take them at the end. We hope you'll share what you learn on social media using hashtag #StatSpeaking. To start us off, we'll hear from JMP Senior Manager of Advanced Analytics R&D, Ryan Lekovitz. Ryan heads the Design of Experiment and Reliability Development team. He earned his doctorate in statistics from Simon Fraser University in British Columbia. He's authored many papers on experimental design and holds several patents that he shares with his team. Ryan will set the stage with some high-level examples of new applications and designed experiments. Welcome, Ryan.
Thank you, Ann. Really happy to be here.
Same. Thanks. Following Ryan, we'll hear from JMP's analytics software tester, Yang Sanchi. Yang received her master's and PhD in statistics from the University of Michigan, Ann Arbor, and North Carolina State University, respectively. Her research is primarily in the areas of stochastic optimization and applications of optimal experimental design to precision medicine. But she's curious about new opportunities as they arise. Welcome, Yang.
Thank you, Anne. It's a pleasure to be here.
Glad to have you. Finally, we're delighted to feature a former JMP intern, Bryce Scott. Bryce is a senior studying aerospace engineering at North Carolina State with a minor in business administration. While interning with us last year, he gained interest in designed experiments and wanted to combine that with his knowledge of the aerospace industry. His intern project was so compelling, he was invited to present it at the Joint Research Conference this past summer. Welcome, Bryce.
Thank you, Anne. Great to be here.
Great to have you here. Let's learn more about these super interesting applications from our experts.
Thank you, Anne, for that introduction. So it's my pleasure to be here today to talk about innovative applications in designed experiments. So now, when I think about what it means to work on the variety of methods that we have in design of experiments in JMP, it often boils down to this idea of making DOE or design of experiments accessible. But so what does that really mean? What does it mean to make design of experiments accessible? And so I would say this idea can take many forms. Right, so sometimes it really is about coming up with innovative ways to introduce DOE to new users. So my colleague, Phil Kay, ran a garden cress challenge that 2 of his children helped out with. And now if you don't follow his hashtag on LinkedIn, I highly recommend following DOE by Phil Kay, because I think weekly he posts different topics in design of experiments. Another one that I did with my daughter was in introducing something called Easy DOE, was whether or not it was easy enough for a 7-year-old. And spoiler alert, Easy DOE is easy enough to teach a 7-year-old how to run a designed experiment. And now we've also had other topics. So you've seen we've had experiments where we've run cars that involve princesses. We've cooked our best hard-boiled eggs, and we've figured out coffee preferences, including from a lot of JMP staff. Now I'll say the other time when I think about innovations in DOE, it also comes with research that happens within our group. Right, so here's just a small sputtering of some of the peer-reviewed papers that we published within the DOE group. Now I'll say, so we're frequent visitors to different conferences. And on top of all of the papers that we publish, we actually also have 24 patents within the group related to innovations in DOE that you actually see within the product itself. Now I'll say, so if you're actually watching this talk, hopefully you're aware of all the resources that we have available. And in particular, when I think of what we have available for design of experiments, so if you look under the application area there, so while I might be a JMP employee, these statistically speaking events and white papers come from thought leaders in a wide variety of fields. And I would say these have relevant information regardless of whether or not you're a JMP user. And so even personally, I found myself going back to these on a regular basis, always finding these useful nuggets of information. But in particular, so one of the things I'm interested in highlighting here today are interns. So this, statistically speaking, it calls out these innovative applications and design experiments. But what I'm really excited about is that we get to highlight work done by interns while they were working at JUMP. So just to give you an idea, this summer JUMP had over 20 interns of various types throughout different groups in the organization. Now our interns do real meaningful work, and they get access to meeting with top executives in the organization. So if you see in the one picture there, you'll actually see John Saul eating lunch with some of the interns. Okay. So I just want to take a moment to highlight the interns in the DOE and reliability group from the past 2 summers. We've been extremely fortunate to have some top-notch PhD students join us, and they've all done innovative work during their time. So Irene G., who was with us last summer and has actually now joined the team as a full-time employee, investigated Bayesian fault localization for complex software systems. That is, for a complex software system like JUMP, if you find a bug, but when you investigate it, it could be one of many different things. How can we use a Bayesian approach to use a test engineer's knowledge and find the cause faster? So now this summer, so we have both Bill Fisher. So he's been investigating demographic targeting and contextualized discrete choice experiments for learning user interface preferences. So that does sound like a mouthful, but this is really about designing a special type of experiment called a choice design, where we can account for demographic information. And in particular, we want to investigate how we might give different context depending on the respondent. And so in particular, if you think of a user interface like something within JUMP, how can we use a designed experiment to be able to test that? And last but not least, so John Miller is looking at initial designed experiments. So when you're planning to do further experimentation using Bayesian optimization. Right? And so this is frequently going to be used in the computer experiment world. And so in particular, though, how are we going to balance doing a good job with both estimating the model or model parameters and maintaining good space filling properties? So now for the stars of today, statistically speaking, I'm really excited that they've agreed to share their innovative applications using DOE. So first up, we're going to have Yang Sanchi discussing a testing problem that not only can be viewed as a design of experiments problem, but it also really requires some novel approaches in testing the problem and figuring out a solution. Now for our second speaker, Bryce Scott, he's going to introduce you to something called supersaturated designs, for which there's really scarce literature on real examples. Now, I do want to point out that the underlying theory is also applying one of those innovations from the DOE team and external collaborators. And you may notice one of the names there is Chris Noxheim, who had a fantastic, statistically speaking, with his daughter. Now, I do also want to point out that Bryce presented on this work at the Joint Research Conference 2024 in Waterloo. And that's a really great conference that's supposed to be stimulating interdisciplinary research and innovative solutions to practical problems. And so there, you'll see a lot of statisticians and data scientists going to that conference. So that really was an honor for him to be able to present there. And so without further ado, here's Yang, who's going to talk to us about using covering arrays, which is really a special type of design to find bugs in software. Thank you.
Hi, my name is Yang, and today I will be talking to you about testing the prediction profiler with disallowed combinations. This is joint work with my colleagues whose names are shown in the slide. Here's a roadmap for the presentation. First, I will talk briefly about software testing, then I'll give a brief overview of the prediction profile and how it works, and what a disallowed combination means in the context of our study. I'll then move on to our testing approach, which leverages DOE. Finally, I'll summarize the main points. Please note that throughout this presentation, I may use inputs and factors interchangeably. So what is software testing? Glanford-Myers offers this definition of software testing, which is testing is the process of executing a program with the intent of finding errors. This is a widely accepted definition in the software engineering community. This definition alludes to the fact that the process of testing should go beyond checking that the software works as intended and instead focus on attempting to break the software so that errors can be identified and fixed before they are discovered by an end user. Since the goal of testing is to find errors, also known as bugs, the focus is on where the bugs could be, particularly the not-so-obvious ones. Boris Weiser offers some insight into where to find the bugs through his famous quote, "Bugs lurk in corners and congregate at boundaries." Software engineers use this quote as a guiding principle. This statement by Weiser implies that bugs in software are usually the result of incorrect implementation involving 2 or more inputs, or the result of edge cases that were not accounted for during the implementation process. Thus, in software testing, the focus should be on test cases that result in failures that are precipitated by the interaction of 2 or more inputs, rather than failures due to individual inputs. The field of statistical software testing is fraught with challenges, and I'll mention some of the principal ones. The first one is the selection problem. In general, due to time and resource constraints, test engineers cannot consider all combinations of the levels of the inputs and must be especially careful in their selection of test cases. The challenge, therefore, is to decide which subset of the possible test cases would be efficient and effective at precipitating failures. Then we have the quality problem. This has to do with being able to determine whether the software is fit for use as testing progresses. Also, test engineers have to determine what the expected outcomes should be for the selected test cases. This is known as the oracle problem. In determining what constitutes an error for a given test case, the test engineer must know what the expected outcome should be. And so any deviation between the actual and the expected results is deemed a failure. In some cases, an alternative software can be used to determine the expected result. In other cases, an analytical approach can be used. In our case, neither of these were viable options because of the complexity of the problem that we had to test. Now to the prediction profiler. The prediction profiler is an interactive tool in JMP that enables a user to explore the relationship between multiple responses and multiple factors. One way of using the profiler is to explore the predicted model of a designed experiment. However, the utility of the tool has grown far beyond this. The profiler displays a set of univariate plots for each factor that shows the predicted response for settings of the factors. The user can interact with the plots to change the factor values and observe how these updates affect the predicted response. The profiler is often used in conjunction with the desirability function, which allows the user to specify the goals for the response. For example, maximize, minimize, or match some target. The desirability function approach is a widely used method that allows for simultaneously optimizing multiple responses by assigning a scale-free score between 0 and 1, known as desirability, and typically higher values are better. So you can think about the desirabilities as encapsulating the goals for the different responses. And so one would like to find the best factor settings that will satisfy these goals, which may be competing. I will now show a video of how the profiler works. In this example, the data set used for analysis consists of 2 continuous factors A and B, and the response goal is to maximize. The beauty of the profiler lies in its interactive nature. So you can see the crosshairs can be dragged to the left or right to change the factor values. And you can also see what happens when the maximize desirability option is selected. We observe that the response is maximized when factors A and B are at 1 and -1 respectively. Now to disallowed combinations. For our purposes, a disallowed combination is a Boolean expression that evaluates to true if a given design point is not in the design space and false if a design point is in the design space. Disallowed combinations generally appear in the DOE suite in JMP, where they are used to create designs in which the runs consist of only points in the allowable region. Disallowed combinations can be relatively simple. For example, a combination of levels of 2 categorical factors, or very complex, a combination of several disallowed combinations resulting in a very complex non-convex design space. Recently, the profiler was enhanced to obey constraints imposed on the design region using disallowed combinations. In this slide, we see an example of a disallowed combination for a design that consists of 5 responses and 2 3-level categorical factors. The combination of x1 at level 1 and x2 at level 1 is disallowed. So you can see that when x1 is at level 1, x2 can only attain levels 2 and 3. Now I'll show a short video to demonstrate the difference between the profiler without the enhancement and the profiler after it had been enhanced to obey disallowed combinations. The dataset consists of 2 3-level categorical factors and 1 continuous factor. x1 and x2 are not allowed to be at level 1 simultaneously. This is the disallowed combination. Now, the first part uses a jump version prior to the enhancement, and straight away you see that this disallowed combination is not on it because x1 and x2 can both attain level 1 at the same time. Also, upon maximizing desirability, the disallowed combination is not on it because the setting consists of a disallowed combination. Now to the profiler after the enhancement. Using the same data set, we will observe that in this particular case, the disallowed combination is on it in that when x1 is at level 1, x2 can only attain level 2 and level 3, and vice versa. We will also see that upon maximizing desirability, the optimal setting is one that honors the disallowed combination. Now to our task. The task was to validate that the profiler was indeed honoring disallowed combinations. The team that was tasked with developing tests to validate the enhancement consisted of programmers and test engineers, most of whom had collaborated toward the fulfillment of the enhancement. In fact, this project had evolved out of previous work that had been done by the team. The team had originally been investigating how to ensure that the maximized desirability option in the profiler obeyed the disallowed combinations specified in the construction of the design. Thus, most of the team had sufficient knowledge and prior information about the workings of the profiler and what validating this enhancement should entail. It's important to note that testing the profiler is not limited to ensuring that the software does not crash when interacting with the profiler. Some aspects to consider in testing the profiler are whether the profiler displays the constrained region correctly, whether the profiler only profiles allowable regions, and whether the maximized desirability option finds the optimum in the constrained space. Some of these features are straightforward to evaluate. Others are more challenging and require more thought and care in determining how to evaluate them. One such feature is testing whether the maximized desirability option has found the optimum, especially when there are multiple responses with different optimization objectives involved. Our goal was to come up with a suite of test cases that were effective in precipitating failures due not only to individual units, but also failures due to interactions between inputs while staying within budgetary requirements. Consequently, the team had to determine the oracles of the test cases that were selected, which, as I previously mentioned, is usually challenging. The team adopted a DOE approach to coming up with the required test cases. This approach to validating software is by no means new. It was proposed by Mallows and Dalal in their 1998 Technometrics paper, Factor Covering Designs for Testing Software, and is known as combinatorial testing. It involves the use of a mathematical construct called a covering array to choose test cases. The use of covering arrays ensures that for a complex engineered system with M inputs, a strength T covering array has the property that any subset of T columns has all combinations of the levels of these columns appearing at least once in the array. The table we see here shows the number of runs, capital N, for a strength 2 covering array given M number of binary factors. For example, given about 1,700 binary inputs, a strength 2 covering array provides 14 runs, which is a great deal more economical than 2 to the 1,700. So a strength 2 covering array ensures that all combinations of the levels of any 2 factors in the design appear in the array. Thus, in software testing, the columns of the covering array are the test inputs, and the rows of the covering array are the test cases. So why covering arrays? Covering arrays are particularly suited for testing because they are cost efficient. When one is limited by time and resources, they are effective for detecting failures while remaining within budgetary requirements. In other words, covering arrays are appealing due to the economical run size. More importantly, they address selection and quality problems that are inherent in software testing. That is, they resolve the problem of selecting a subset of test cases when faced with a vast number of possible test cases. They also help in uncovering failures that are a result of interactions between multiple factors that could have otherwise gone undetected if only individual units are being tested. So they go beyond the one factor at a time testing, which most people do. They also provide a disciplined and defensible approach to testing, as opposed to the relatively uncontrolled approach of simply testing more. So after deciding upon this approach, what remained for the team to do was to identify the inputs, that is the actual aspects of the profiler that should be tested, and identifying the values of each input, that is partitioning the values for each input in an appropriate way. Now, due to the unavailability of a varied set of data sets with which to exercise the profiler, the team was faced with the challenge of ensuring that a sufficiently wide range of possible input types were accounted for in the testing process. To address this problem, the team decided to combine the dataset generation and test case selection problems. This idea of a combinatorial testing approach that addresses dataset generation and test case selection in one step is a novel one. There were many possible factors to consider for dataset generation and test case selection. After much deliberation, the team settled on 15 dataset generation factors and 3 test case selection factors. In effect, we had a dataset of datasets. That is, each row of the test suite contained settings that were used to generate a dataset, which was then used to test the profiler. Here are the dataset generation factors and test case selection factors and their levels. The first 15 factors determine the datasets that are generated. These datasets will have some number of factors, some number of responses, different constraints, both linear and nonlinear, and other pertinent factors. The last 3 factors are the test case selection factors, and these are inputs that pertain to the profiler feature itself. The previously shown dataset generation factors and test case selection factors result in over 1 million test cases, which is simply not a feasible testing task to undertake. However, a strength to covering array resulted in 13 runs in which all pairwise combinations of the levels of the factors appear, and all 8 combinations of the levels of the profiler inputs are accounted for. Now that is what I call the magic of covering arrays. Now to the sequential nature of testing. The team went through several iterations of testing after the initial testing phase. This helped to catch and address a fair number of subtle failures. For example, anomalies in the profiler traces when the design matrix is singular. This was done using the nightly test stream of JUMP for regression testing, which seeks to ensure that the software continues to behave as intended after alterations in code. We also revisited the oracles to make sure that the expected outcomes that we decided upon were indeed appropriate. Subsequent meetings after the initial test phase resulted in ideas to improve the test suite, such as generating larger data sets, using data sets that were not generated using the custom designer and JUMP, trying different specifications of the disallowed combinations, changing the settings for the genetic algorithm options, among others. So, a recap of the highlights of this presentation. Testing statistical software is challenging because deriving oracles is difficult in many cases, and sometimes there are not enough varied data sets to ensure adequate coverage for the different possible ways in which a feature may be used. The use of combinatorial testing is efficient as well as effective because one can catch faults that arise due to the interaction of multiple inputs and not just individual inputs. Also, it is a more principled approach to software validation compared to one factor at a time testing. This project revolves around the novel idea of combining dataset generation and test case selection and testing the profiler with disallowed combinations using a DOE approach. If you want to know more about this project, check out our paper in the Journal of Quality Engineering. Thank you for your attention. I'll now hand over to Bryce to talk about his application of group orthogonal supersaturated designs.
Good afternoon. My name is Bryce Scott, and welcome to our web series about design of experiments, specifically group orthogonal supersaturated designs.
So just as a quick summary or a little bit of an introduction to what we're going to get into, what we've got pictured over here is what's called a benchmark test for a printer. And this is not an aerospace part. This is just something that you print to test the quality of your printer and just see how it's doing. So if we look on the left over here, we were able to use a special type of design of experiments called group orthogonal supersaturated designs. And on the left over here, this 106 minutes, 24 out of 30 quality score is what we were able to achieve using the optimal settings, which we found out using the design of experiments, compared to on the right over here, 196 minutes, 22 out of 30 quality score is what the default printer settings are. So if you just plugged in the printer and press print, this is what you would get on the right, versus on the left if you used a DOE to get the optimal settings. So more of just a quick introduction to what we were able to optimize with the DOE. If we look over here, we have a graph which is total cost per model, and then at the bottom is quality per model. So this is all of the tests that we did, including the optimal and the recommended settings, which is just the default settings. And you can see that we were able to come in with the highest quality and the lowest cost compared to everything else. And that is evident in our little highlights over here. So how does 3D printing fit into aerospace? So we've got a little bit of a summary from some big companies within the aerospace industry. General Electric over here saying 3D printing for jet engines and 3D printing in space. Over here, we've got some information from NASA. This is actually pretty cool. So 3D printing allows you to use some previously underutilized materials, and since 3D printing kind of uses a melting method to get the materials, you can use some really interesting materials and you can get pretty creative with your material properties. And over here, we've got some prototyping used in a landing gear configuration just to test the geometry and make sure the mechanical systems are working with each other. And here, this is a company called Hubs, and Hubs is actually a 3D printing company who outsources their 3D printing. And this is a cross-section of a jet engine over here that they were able to print. It's difficult to visualize things on a computer. It's a lot easier to see how things work together when you've got a physical model. But, when it's a jet engine, you can't just have jet engines lying around to mess around with. Whereas 3D printing and very high quality 3D printing is very helpful, in order to visualize this kind of thing. And another interesting kind of case study over here is a way that you're able to use more complicated geometries and more sophisticated geometry. In traditional manufacturing methods, it'd be very difficult to make something like this on the right over here. You would rather make something like this on the left, lots of flat edges and corners. So what they were able to do, this is from Airbus, is they got this original bracket, which is a satellite bracket, and then they used something called finite element analysis, which is just a way to see where the stresses are lying within your product. And they were able to draw up this exoskeleton looking thing in the middle. And then all of this kind of white area here, they just took that away. And then they were left with this on the right. So previously, this would be impossible to create, but now with the use of 3D printing, they're able to make a lot more complicated geometries that is, if anything, is probably stronger, and it uses far less material. So what are some of the challenges when it comes to 3D printing? So this is just a summary of some market research that says, what are people's problems with 3D printing? We've got things like technology limitations, cost of material is something that we address. Quality, there's no point using 3D printing if it's bad quality. And then no in-house expertise. So this no in-house expertise is really something that we are trying to focus on with this DOE is, you get this 3D printer and it's kind of like this black box. You have no idea what this myriad of settings means and how you ever supposed to figure it out. Whereas if you use a DOE, you're able to get information on all of those factors and you're able to make decisions based on exactly what those factors mean for you and how they get your output. So some common 3D printing problems. Over here, we've got something called ringing, which is, there's over extrusion when accelerating, leaving visible ripples or waves is this kind of surface quality finish over here. Then bed non-adhesion. This is kind of just when the bed might be too cold and the edges of the bed of the print don't stick to the bed. And in 3D printing, your current layer is only as good as your previous layer because they get printed on top of each other. So if you've got something like this all the way at the bottom of your model, you're going to get a bad model no matter how good the rest of the print is. And then over here, we've got something called stringing, which is kind of where the nozzle over extrudes and you get these little hair-like fibers between your models. So some of the limitations are materials. As I said earlier with the NASA example, there's a lot of materials that you can choose from, but getting them to be printable and the feasibility of these materials is something that is quite a big challenge. And then cost, and again here, no in-house expertise, which is something that we are trying to address over here. So we were able to use a design of experiments, which is a group orthogonal supersaturated design. So what is design of experiments? Maybe that's a completely new term to you. So a quick way that I like to describe what this is with this little picture over here. So imagine that you are one of these two scientists, and your boss comes to you and says this output line right over here needs to be straight or some kind of curve, whatever it may be. And you know that these levers over here somehow have an impact on that model, right? So if you need it to be curved, let's say like it is now, you might think, all right, well, the configuration that it is now is perfect, but let's try and figure out some more configurations. So then you move this first lever and then everything changes. Now it's completely loopy. So you think, all right, well, this first lever has to be up in order for everything to be good. Then you start changing these other ones, and no matter what configuration you choose, it just is never curved or is never the way that you want it. So there is no way for you to know exactly which one of these levers is causing that or which combination of these levers is causing that. So probably what you would do is something called OFAT testing, one factor at a time. And that means you would go and manually do each lever at a time and you wouldn't test any interactions. Now that's okay if you have, one or two variables. But imagine instead of just these 5 levers, you had 100. And instead of this little line on a screen, it was a rocket engine or something that cost millions of dollars to test. There's no way you would do OFAT testing. So what you need to do is something called the design of experiments, and more particularly a group orthogonal supersaturated design, which tests groups of inputs instead of just singular inputs by itself. And then you're able to get information on all the inputs as if you had tested them by themselves. And really the biggest benefit of a Go SSD is that you can test, let's call it 30 numbers of factors, and you can get information on all 30 in less than 30 numbers, in less than 30 runs. So the number of factors is 30, and you can get information on all 30 factors in less than 30 runs. And that's really the biggest advantage of a Go SSD. So what does our setup look like? Over here, we can see what the setup looks like. And this down over here is our factor grouping. So we group these factors. This is kind of where some domain expertise comes into play. You would want each of these groups over here to have one important factor per group. Now, if you didn't know which were the important factors, you could just let it be random. But if you knew, you would put them in each of these groups. And these gray dots over here are showing you how correlated these factors are. And then this is just a list of all of our factors and all the different variables. So we went and we then tested this a whole bunch of times. And what we were able to get was some pretty interesting results. And here I can show you just what one of these little test prints looks like with a time lapse over here. So as it prints, we can kind of see all the different structures forming. At the moment, it's just doing the bottom. And then eventually it'll get to some overhang testing, which is kind of where it's printing on thin air. And then we can also see some cylinders, and what's called bridging is where it prints a little bridge. Not super complicated. And then there's some holes that it's testing, and then some pillars on the right-hand side is something that it tests as well. Right. So then if I open the factor analysis results sheet, you can see this is our test setup, all of the different variables and all of the different tests. And then at the end, we have our quality scores and how long it took for each print. And now the way that the quality scoring worked is it was a little bit subjective. I went in and I rated each of the different factors involved in the test, such as overhang, the cylinder testing, the holes, bridging, stringing, and surface finish to get an overall quality score out of 30. And then the time was simple. It's just exactly how long did it take for the time for it to print. So what we can do with this information is we can fit certain models to try and optimize our settings in order to get the best time, for example. So if we look at this, what this is telling me over here is that these are all of the factors that are important for time. And then these are my p-values, so kind of how important or how random they are. And then these red bars are also telling me how important they are. So if they fit in within the red bars, they're more important. So then what I can do is I can come down here to my profiler, and my profiler is telling me, if you want to have maximum time or minimum time, these are the settings that you should do. So what's listed here in red, this is exactly how I should set up my printer in order to get some desired time. And this time will be listed here in red, which in this case it's set to a maximum, but we would want it to be a minimum. So I can do the same thing for quality, which is right over here. So what this is saying is these settings over here is what is important for my quality score. And then if I scroll down, I have this profiler again. So I can move these things around and I can kind of move these error bars to try and see exactly, what my quality will be. And as you can see, everything is changing as I'm moving these settings. So in this case, we wanted time and quality. So what I can do is I can create something called a combined profiler. So now I've got time and quality. So here, these are the important factors for time. And if I scroll down, I'll get the important factors for quality. And then if I keep going down, I'll get something called my combined profiler. So now it's combined all of the important factors for quality and all the important factors for time, and it's put it in one. And I've set this desirability to be maximum quality, which is telling me is 25, with a minimum time, which is telling me is 93 minutes. So now let's say, one of these settings you knew, for example, had to be on. So right here, we've got print cooling. Let's say I know print cooling must be off. So I set that to off, and it automatically re-optimizes all of the settings based on that change that I just made. And I can see that in the change in these red settings right over here. And then it's telling me, okay, you're going to get about 23 for quality, and you're going to get about 61 for time. So this is how we were able to then use these settings and go in and actually print the optimal quality setting. So here's some highlights from all of the testing that we did. And in this case, we can see test print number 8 was one of our best quality prints. We got a 23 out of 30, but 204 minutes. Whereas our optimal settings was 106 minutes, so about half and a better quality score. So if we look, it's just a different view. We can see not a whole big difference in terms of quality, but a really big difference in terms of time. And yeah, this is the default settings like we showed earlier. So if you just bought the printer, plugged it in, press print, this is what you would get on the right compared to this on the left, which is a big saving in time. Here's one of our lower quality prints, 377-minute print, which is so 3 times longer than our optimal settings, and a quality score of 17 out of 30. So not too great either. And we can see that we've got some stringing right over here as well. So this is test print number 15, which is our worst quality print. We can see 3 out of 30, 224 minutes. And we can see this print quality is very, very bad. Here's just a different view where you can see some pretty major differences between that. So if we go down, just to reiterate, if we look right over here, we can see that our optimal settings had the lowest print cost with the highest print quality. And if we compare it just across the line, we can see that it beat them all in terms of high quality and in terms of low price. And that's evident right over here. So how do we use this? What do we do with this? And for the purposes of this case study, we were printing just little test bed models. But this over here is something called an impeller, which is a pretty common part within the aerospace industry. And you can see that it's got a lot of overhangs. So for example, with the DOE, you can optimize based on any output setting. So we could have optimized based on purely overhang performance, and we could have printed the best version of this, for example. And you can really do it with anything. If you know what your geometry of your print is going to be, you can optimize based on that print.
Thank you for watching, and I hope that this short presentation was able to give you an insight into some of the capabilities of JMP and really some of the capabilities of utilizing DOE and how it can, make things more efficient and really give you kind of an insight into what your data means and an insight into how a process works. And, we look forward to any questions you may have, and back to you, Anne.
What great examples to extend applications of DOE to derive more value. Thank you, Bryce, Ying, and Ryan. Reminder to the audience, if you have any questions, please submit them. And we do have some questions already, so we're just going to dive in. Ryan, it looks like the first question is for you. What areas of research in DOE do you see as especially promising?
Oh, that's how long do we have? So when I get asked that, I'd say a couple that jump to mind. So the first has to do with that idea of sequential experimentation, which I think some of the words that you hear a lot these days, so things like Bayesian optimization and active learning really play into that, which really says, after I've done my first experiment and I'm ready to move on to the next step, what should I do next? And so when you think about it, inherently, that is actually a design of experiments problem. It says, for these inputs or for these factors that I have, what do I want to do next? I'd say the other thing that I see a lot of activity in would be big DOE. So I think traditionally when I think of design of experiments, it's really small data, smaller numbers of factors, and a small number of runs. So like in some of these examples that we saw today, sometimes big DOE means a lot more factors, right? So if you think of these complex systems, you may have hundreds to thousands of inputs. The other thing is sometimes numbers of runs. Sometimes I may think 24 runs sounds like a lot for some experiments, but nowadays we're talking about hundreds of thousands of runs that we may have. And so how do we start thinking about designs for cases like that?
Very good, thank you. A lot of exciting things. It looks like this next question is for you, Yang. Do most software companies use covering arrays as part of their software testing strategy?
As far as I'm aware, and the answer is unfortunately no. Most software companies, I would say, use random testing more often, what is referred to as fuzzing in the software engineering world. And in fact, earlier this year, in February, NIST organized a conference, a workshop that brought together many thought leaders in the area of the semiconductor industry, so in government, industry, and academia. And all through the workshop, they were making mention of random testing, fuzzing, and very cursorily mentioned combinatorial testing. It was actually in the last presentation of the workshop that combinatorial testing was mentioned. However, I should say that NIST is a strong advocate for combinatorial testing. And so hopefully with time, more people will get on that boat and we should see better results testing-wise.
Thank you for that. And I just can't help but think about, in theory, based on what you shared, it seems like there was a strong likelihood that that $400 billion outage that we experienced recently could have perhaps been avoided. Were they just aware of covering arrays?
Well, perhaps if the faults were due to interactions between inputs, so say the fault was narrowed down to the interaction between two inputs, then definitely a strength 2 covering array would have identified that fault, and that could have been averted. That disaster or the loss could have been averted. But well,
wow. We have to get the word out.
Definitely. I am a strong advocate for combinatorial testing. It really is very efficient and effective. And I think that the more it is used, the better confidence we will have in all the software that that is in use in all of these gadgets that we really take for granted. We believe and trust that it's working as expected, but not really.
Right. It's a very strategic approach, as you pointed out. Thank you. And Bryce, we have a question for you. curious if you shared your optimal 3D printing settings with the manufacturer.
So the answer is no, we didn't. And one thing when we first did the project was that we went and looked to see if any of the manufacturer of either the software program or the printer kind of submit what their optimal settings are or what the settings mean. And we actually weren't able to find that either. So in the video comparison, we did do a default settings print, and that's kind of where you just plug in the printer and press print, But one thing that's interesting that I did want to mention is that what we optimized was not necessarily the printer itself. There's something called a slicing software, and that's essentially just what converts a 3D model in the computer to a set of instructions for the printer. And that slicing software is not unique to the printer. So we optimized the slicing software. So hypothetically, if we put in a different printer, the results might be different. Or if we use the same printer and put in a different software program, the results could be different for that too. So maybe we'll have to refresh the DOE and use different printers.
Very interesting, fascinating, and heavy engineering focus.
Yeah.
Well, so we don't have any audience questions, so I would like to encourage our audience members to submit some questions because we've got some expertise here that we could further share some of their wisdom and knowledge in these approaches to get the most from your data, because to me, design of experiments is about learning the fastest you can from your data, and it's getting information rich data versus a lot of the observational data that are out there that are more information sparse. So we'll give a few more minutes, but actually let me ask you, Yang, is there a question you're commonly asked when you present something about covering arrays?
Well, actually one question that I recall getting when I presented this at some other conference was why do we focus on, say, strength 2 covering arrays or lower T is what we call it, so strength T, right? So why do we choose lower values as opposed to higher values? And it actually is because faults due to lower order interactions are more prevalent than the higher order interactions. And empirically, it has been shown that there are very few cases where faults are due to more than five-way interactions, right? So in at least in the software engineering community, it is a well-known fact that about 80% of faults are due to two-way interactions, two-way combinations, rather than higher order ones. And so that is why we typically go for the strength 2. In some cases, you can go for strength 3, which is also still economical, but with higher number of runs. And you can be assured that if you use a strength 3 covering array, you would get really you get 100% coverage for 3-way interactions and a pretty high coverage for 4-way interactions as well. So yeah, that's one of the questions.
Super interesting. Thank you for sharing. It really pays to look at the data to hone your approach to solve the problem. A lot of thought goes into that. I appreciate that. Okay, so if we have no questions, then I want to thank you all again, Brian, Ying, and Bryce, for sharing so much interesting info with us and your projects and your plans. And I appreciate the appreciation from the audience. Thank you also for joining us. And we hope these innovative applications of DOE inspire you to try new ways to solve problems, because how you solve problems, how well you solve problems matters. It's key to maximizing efficiency and effectiveness. To see more innovative applications of designed experiments, we invite you to join us for the next episode of Technically Speaking, where another one of our thought leaders, subject matter experts in this area, Tom Donnelly, will share with you how you can use DOE to reverse engineer formulations. So we'll get that link in the chat to you. And for more events like this, you'll find a variety of topics at jump.com/statspeaking. Thanks so much for watching, and see you soon.